Hello and welcome to our second lesson on binomial theorem. Today we will focus on proving binomial theorem for positive integral index n using principle of mathematical induction. I think you have mastered principle of mathematical induction in a previous chapter, right? So, let us see how that helps us to prove the result which we had introduced you to in our earlier lesson. Let us see what the theorem is once again, try to recall and then get started with the proof. Binomial theorem for positive integral index n suggests that a plus b whole to the power n is equal to NC0 a to the power n plus NC1 a to the power n minus 1 times b plus NC2 a to the power n minus 2 times b square, so on up to NCR a to the power n minus r b to the power r plus so on till the last term, that is NCN b to the power n, where of course NCR is nothing but n factorial divided by the factorial of n minus r into r factorial. We have talked about this theorem and we understood in the last lesson that if the index is n, there are going to be n plus 1 terms in the expansion. NCR a to the power n minus r b to the power r is the general term which is in the position of r plus 1. If you try to generalize the pattern here, you will realize that the first term had the binomial coefficient as NC0, right. Then we are looking at NC1, NC2. So, if you take the lead from there, perhaps you will agree that NCR a to the power n minus r b to the power r should be in the position of r plus 1. Now, today as I said, we will focus on proving the result. The proof of this result depends on two other sub results which suggest that NC0 is equal to NCN is equal to 1. Now, there is nothing new in this result. If there are suppose n elements and I choose nothing, in how many ways can I do that? Obviously 1. If there are n elements and I choose all n, one way only. You may algebraically calculate the same expressions and you will find that yes, NC0 and NCN irrespective of what n is will always take the value 1. Now, it is the second result which actually is going to help build up the proof of this theorem. Second result says that NCR plus NCR plus 1, when I add these two coefficients, I end up with n plus 1 CR plus 1. Now, the proof of this result is nothing but algebraic simplification, but we must try it out and see if it does work. So, here it goes. Let us start with our left hand side, that is NCR plus NCR plus 1. If I expand it in terms of factorials, I get n factorial by n minus r factorial into r factorial plus n factorial upon n minus r minus 1 factorial into r plus 1 factorial. Now, to simplify this, we can always take out some common factors. So, let us try to rewrite this. What you can do always is, whenever you work with factorials, is to rewrite the larger of the two factorials. So, in this expression, if you observe between n minus r and n minus r minus 1 factorial, n minus r is a bigger number. So, if I expand n minus r factorial, it will break down to n minus r times the factorial of n minus r minus 1. R factorial and r plus 1 factorial if I compare, then obviously r plus 1 factorial as I expand will break down and rewrite as r plus 1 times r factorial. Now, once I have done this, you can see that there are certain common terms which I can pull out of this sum. So, I have n factorial upon factorial of n minus r minus 1 factorial times r factorial. These are the common terms between the two, and then I am left with only the sum of 1 by n minus r and 1 by n r plus 1. If I now continue with taking the LCM and simplify, I am left with n plus 1 by n minus r times r plus 1 and the quantities which I had taken out common earlier. I am sure you can now recognize that numerator, because it is product of n plus 1 and n factorial, is nothing but n plus 1 factorial. In the denominator, n minus r minus 1 factorial into n minus r turns out to be nothing but n minus r factorial, and r plus 1 times factorial of r combines together to be rewritten as r plus 1 factorial. Now, if I rewrite this expression, isn't that what n plus 1 c r plus 1 will be? Agreed? And that is what our second result was about. So, this result is helpful when I combine two terms in NCR form. Recognize I am looking at NCR plus NCR plus 1, and it amounts to shifting that n to n plus 1 CR plus 1. We will refer to this result as we proceed. Let us start with the theorem. Since I said earlier, we are going to use principle of mathematical induction. So, I am bringing the terminology of mathematical induction in. I am going to call the result as P of n. So, the mathematical statement is being addressed as P of n. Of course, there is a equation here, left hand side and right hand side. We want to prove that this is true for all n such that n is a positive integer. Principle of mathematical induction breaks down to 3 steps mainly, right? Basic step, and then assumption, and then induction. So, basic step is to verify whether the result is true for n equal to 1. Assume that the result is true for n equal to k, where k is any natural number, and then using that assumption, if you can prove that the result is true for k plus 1, then principle of mathematical induction states that result is true for all n belonging to natural numbers. So, let us start with basic step. Is this result true for n equal to 1? Yes, right? If I take the left hand side of P of 1, it is nothing plus but a plus b to the power 1, which is a plus b. Right hand side of P of 1, when n is 1, the right hand side is nothing but 1 c 0 a to the power 1 plus 1 c 1 b to the power 1. Both 1 c 0 and 1 c 1 are simply 1. So, it is equal to a plus b. So, we say P of 1 is true. Assumption step, let P of k be true, where k is a positive integer or a natural number. That means a plus b to the power k has an expansion of the form kc0 a to the power k plus kc1 a to the power k minus 1 times b plus kc2 a to the power k minus 2 times b squared plus so on up to kck b to the power k. While writing these expansions, keep the two simple facts in mind. Power of a will reduce, power of b will increase by 1 in each successive term. Also, the sum of the powers of a and b will always be the index, isn't that? So, that means k minus 2 plus 2 must always add up to the same number as k. So, that is a kind of a check when you expand binomial theorem. And using this, I am going to now prove that the result is true for k plus 1. That is, I want to show that a plus b when raised to the power k plus 1 must give me the same expansion when I replace n by k plus 1. So, to prove this, of course, I start by rewriting a plus b to the power k plus 1, and in this case it can be rewritten as a plus b times a plus b to the power k. This a plus b to the power k gets replaced by the expansion that we had assumed, because our result was assumed to be true for k. Now, as I open up this entire product, I work a little more carefully, and with that little precaution things will become easier. So, I am not going to expand just blindly. What I am going to do is, I am going to take this a plus b and very carefully multiply it with the first term of the expansion of a plus b to the power k. So, what happens? We will see in a minute, but keep this fact in mind. Similarly, I will multiply a plus b with the second term and so on. Now, if you start doing that carefully, you will realize that you will get an expansion of the kind kc0 a to the power k plus 1, right. Then when b gets multiplied with the first term, you will have kc0 a to the power k times b. Similarly, when a plus b gets multiplied with the second term, so first a gets multiplied and therefore the power of a increases, that is, I will have kc1 a to the power k times b plus kc1 a to the power k minus 1 times b square. Now, power of b has increased, and so on. So, take a minute to write this very carefully. This is the most crucial step of the proof of the binomial theorem. Once this goes wrong, then you will be finding it very difficult to simplify and get what we want. So, be very careful. Now, what is the next thing to do? Can you see certain like terms in this expansion? Surely you can. You will be able to see that the second and third term, as we expanded, they are ending up to be like terms. Similarly, the fourth and the fifth, they are like terms. So, we are going to now collect like terms, and on collecting like terms, I get the expansion to be kc0 a to the power k plus 1. Between second and the third term, a to the power k times b is common. So, I am left with kc0 plus kc1 times of a to the power k times b. Between the fourth and the fifth term, a to the power k minus 1 b square goes out, and I am left with kc1 plus kc2, and so on. But you must write at least the next term, which is with the coefficient a to the power k minus 2 b to the power 3. The terms collect and become kc2 plus kc3 times a to the power k minus 2 b cube. Now is when we bring in our two results. The first result which said that NC0 and NCN, no matter what n is always 1. The second result says that NCR plus NCR plus 1 is going to become n plus 1 CR plus 1. So, now can you see that our first and the last term, which had a kc0 and a kck, they can always be rewritten as k plus 1 c0 and a k plus 1 c k plus 1. So, I can rewrite those coefficients. At the same time, the terms that I have collected, you can see the second result helping us to rewrite. So, I am looking at kc0 plus kc1. So, using the second result, kc0 plus kc1 becomes k plus 1 c1, right? And therefore, our next term as well, wherever I have a kc1 plus kc2, the index will shift to k plus 1, and I will pick between the 1 and 2 the higher number 2. So, using both the result 1 and 2, this expansion gets rewritten as k plus 1 C0 a to the power k plus 1 plus k plus 1 C1 a to the power k times b plus k plus 1 C2 a to the power k minus 1 b squared plus so on, and the last term is k plus 1 c k plus 1 b to the power k plus 1. So, isn't that what we were aiming at? We were looking at proving the p k plus 1 to be true, and this has been proved based on the assumption that the result was assumed to be true for n equal to k. So, in language of principle of mathematical induction, we conclude by saying that p k plus 1 is true whenever p k is assumed to be true, and therefore, by principle of mathematical induction, the result must be true for all n where n belongs to natural numbers. So, in this case, that is how we conclude. Therefore, the result is true by principle of mathematical induction for all n belonging to n, and therefore, the binomial theorem is proved. Now, this result, as we proved it, is based on principle of induction, is requiring right now a lot of simplification and a very directed simplification. Once you rewrite it on your own, you will find that there is really nothing difficult about it. So, I hope you have understood and you have followed this proof, and you are now ready to start attempting some problems. In order to try and be good at doing those problems, it will help to put certain facts together and hold on to them. Some observations about binomial theorem. Binomial theorem lets you understand that every time you expand a plus b to the power n, the total number of terms are going to be n plus 1. At the same time, power of first quantity decreases, power of second quantity increases in each successive term, and the total power of the a and b, that is first and the second term, is always same as the index of the expansion. At the same time, the general term T r plus 1, the r plus 1th term, is given by NCR a to the power n minus r into b to the power r, where NCR is n factorial by factorial of n minus r times r factorial, right. Now, with these little facts but significant facts, we are ready. So, let us start with our first question. The question says find the 13th term in the expansion of the binomial given here. So, I am looking at 9x minus 1 by 3 times root x whole to the power 18. We are not interested in the entire expansion. We are asked to find only the 13th term. Okay? So, here in this case, let us identify what is n, a, b and r. N of course is the index, so that is nothing but 18, and a, the first term, is 9x, b is negative 1 by 3 root x, r is 12, not 13. Keep in mind that we are now going to look at the use of general term Tr plus 1. So, in Tr plus 1, r plus 1 is 13, the 13th term. So, r will take the value 12. Once you have these facts in, then it is nothing but substituting these values and simplification. So, for us T13 turns out to be nothing but 18C12 9x whole to the power 6 into negative 1 by 3 root x whole to the power 12. So, now it is time for you to do some work. Simplify each one of these and see if you end up with a number. There is going to be no x coming in because the powers of x are all going to get cancelled. So, I am getting an x to the power 6 and I have in the denominator x to the power 6 as well. So, this is definitely a special term which does not contain an x in it. It's only 18,564 as a number, and it has a special name. Any term which does not have an x in it, the power of x is 0, is known as absolute term or term independent of x. So, we will be using and may be asked to find a term independent of x. In this case, it happens to be the 13th term which has no x in it. So, it is only substitution that has given rise to this answer. One more question. How do I find the value of 999 raised to the power 4? And of course, no calculators or computers here. So, how do I use binomial theorem here? Obviously, first write 999 as a binomial, and the best binomial that I can think about perhaps would be writing it as 1000 minus 1, isn't so? So, let us start by rewriting 999 as 1000 minus 1 and see what 999 raised to the power 4 would start looking like. So, rewriting 999 to the power 4 as 1000 minus 1 whole raised to power 4 and applying binomial theorem, I get 5 terms where I can see that the first term of course is 4c0 1000 raised to power 4 minus 4c1 1000 raised to power 3 times 1 plus 4c2 1000 raised to power 2 into 1 squared minus 4c3 1000 raised to power 1 into 1 cubed plus 4c4 1 to the power 4. Now, just take another minute or two to evaluate each of these terms, that is mainly you need what is 4c1 and 4c2 and 4c3, and then multiply with these numbers and you have 5 terms which add and subtract and give you a big number, more than 900 billions. So, without any calculator or computer, we are in a position to expand, get higher powers of large numbers as well using binomial theorem. So, this question illustrates just one of the possible use of binomial theorem. Here is another example where we will use the binomial theorem to find middle term of a certain expansion. So, the question says find the middle term in the expansion of x squared plus 3 by root x whole to the power 10. Of course, x greater than 0 to keep root of x, square root of x defined. So, here the focus is on first identifying which term would be the middle term of this expansion. So, if you notice, the index of the expansion is 10. How many terms are there in the expansion? Not 10, 11, right? One more always than the index. So, what would be the position of the middle term? If there are 11 terms, the middle term will be the 6th term. So, in other words, they are asking us to find the 6th term of the expansion. So, that is just a little twist in the problem and we are ready to go. So, we are looking at 11 terms in the expansion, middle term is the 6th term. So, we have to find T6. Again our general term TR plus 1, NCR a to the power n minus r b to the power r, and therefore, if to find T6, r will take the value 5. So, n is 10, a is x squared, b is 3 by root x, r is 5. So, if I substitute it in the formula of TR plus 1, T6 takes the value 10c5 x squared raised to the power 5 into 3 by root of x whole to the power 5. Little bit of work in terms of simplification of course is required. So, you can expand 10c5 using 10 factorial by 5 factorial into 5 factorial, and when you simplify the powers of x together and the constants, you would end up with the final answer. In this case, it is same as 61,236 times root of x raised to the power 15. So, In other words, as you look back at the 3 questions that we have done today, the observations that we have made regarding the binomial theorem and the expansion that we get as a result of it are going to play a key role in solving the problems. So, go home and try some more problems based on what you have learned today. Practice solving, proving the binomial theorem on your own, and you will be set to take up more challenges in our next 2 lessons. See you.